Welcome. Today, we're going to use AWS ECS, or Elastic Container Service, to deploy a highly available Apache Web Server container. Containers have become a cornerstone of modern application development, allowing us to package our applications and all their dependencies into a single, portable unit. With ECS, AWS makes it simple to orchestrate and run these containers at scale. ECS is great for running containerized applications because it eliminates the need to manage the underlying infrastructure, whether you're running microservices, batch processing, or web applications. ECS gives you the flexibility to run containers in a way that fits your workload and budget. In this video, we'll walk through building an ECS-managed application to host an Apache Web Server instance using the AWS Cloud Development Kit. This will include setting up the networking, creating the container service, securing it with SSL, and making it accessible via a custom domain. By the end, you'll not only have a running application, but also understand the key components of ECS configuration. AWS offers several ways to deploy ECS resources, including pre-built patterns for simplicity. Today, we'll take the manual route to define each construct, so you get a full picture of how the pieces fit together. Let's get started with setting up our AWS CDK project. We'll create the project directory, initialize it, install the necessary dependencies, and open it in WebStorm for development. Start by opening your terminal, where we'll run all the commands for setting up the project. Let's create a folder for our project and navigate into it. Use Yarn to quickly set up a packaged JSON file for dependency management. Install the AWS CDK libraries and TypeScript types for Node. Next, we'll open the project in WebStorm. Next, we'll copy over two configuration files. These are common files that are used to set up the project to work properly with both the CDK CLI and the TypeScript compiler, providing the foundation for defining and deploying the infrastructure as code. We won't go into detail on these files for now, as they are standard for AWS CDK projects. Now that the project is set up, let's start building the structure of our CDK application. First, we'll organize our project by creating a source directory for source files and adding the main entry point for our CDK project. This will lay the foundation for our ECS stack. Here, we're creating a new CDK app and calling the synth method, which will eventually generate a CloudFormation template for our project. Next, we'll create a new file where all the infrastructure code for our ECS Fargate solution will go. We'll soon define the logic for this. Awesome work! We've set up the entry point and created a new TypeScript class to house the infrastructure code. In the next steps, we'll flesh out the ECS Apache Web Server stack to define the infrastructure for our demo. It's time to start coding. We'll define a class that extends the CDK base stack class. We'll define the method signature for the constructor, which includes the scope, ID, and custom props. Because we're using a custom set of props, we'll create a new interface that extends stack props. This is a base interface that provides additional properties that our stack requires. By the end of the video, we'll have added 4 properties to this interface. Next, we're going to talk about how to reference existing AWS resources in your code. Sometimes, you don't need to create new resources, but instead want to use resources that already exist in your AWS account, like an existing VPC, Route 53, hosted zone, or a secret from Secrets Manager. To reference existing resources in CDK, we use special methods. These methods allow you to fetch and use resources that were not created in your current code. Let's walk through some examples. We can use VPC from lookup method to reference an existing virtual private cloud. This is particularly useful when you want to deploy new workloads into an existing network setup without creating a new VPC. To work with an existing Route 53 hosted zone, you can use the hosted zone from hosted zone attributes method. This lets you connect to a domain that's already managed in Route 53. Great for configuring DNS for new services. If you need to pull in an existing secret from AWS Secrets Manager, use secret from secret name v2. This is perfect for securely referencing sensitive information like database credentials or API keys without hard coding them in your code. Now, we'll reference an existing VPC in our AWS account and integrate it into our stack. This step ensures our ECS service is deployed into the correct network environment. Let's update our code to use the VPC from lookup method and define our first custom property in our props interface. Within our ECS Apache Server Stack props interface, we will create the first property called VPC ID. This will be of type string and will be used to pass the unique identifier of our existing VPC into the stack. Next, we'll create a reference to our Route 53 hosted zone. We'll go ahead and create the reference now, but we'll need to also update the props interface to include both the hosted zone ID and the zone name. We'll use the hosted zone from hosted zone attributes method and pass in the unique identifier for the existing hosted zone and the domain name of the zone. This makes it possible to configure DNS settings for the application deployed within the ECS service. Next, we'll add two new string properties to our custom interface. First is the hosted zone ID and the zone name. These values will be passed into the stack from the main TS file. The last of our existing AWS resources that we'll reference is the Docker Hub secret stored in AWS Secrets Manager. This secret contains the credentials needed to authenticate with Docker Hub for pulling container images. We can reference the secret with the secret from secret name v2 method like this. This gives us secure access to the Docker Hub credentials stored in Secrets Manager, which we can then use in our ECS task definition to pull the required container images. This approach ensures sensitive information is handled securely and never hard-coded in the stack. Just a reminder, the Docker Hub credentials aren't required, but it could help with avoiding rate-limiting issues and is needed if you want to pull from private repositories. We're using it here for demonstration purposes. Now that we've created references to our existing VPC, hosted zone, and secret, the next step is to secure our application by creating an SSL certificate using AWS Certificate Manager. This will ensure all web traffic to our application is encrypted, providing a secure connection for users. We'll use the new certificate method to create a new cert. We'll provide a unique name to make it easily identifiable in the Certificate Manager console. We'll assign the domain name of demo.pixelwake.com to the certificate, making sure it's tied to our application's hosted zone. Finally, we'll use DNS validation for authentication. This involves creating DNS records in the hosted zone to verify domain ownership. Once created, this certificate will be used with our application load balancer to enforce secure connections to our ECS service. Back in the code, let's create the certificate using the AWS CDK. This will ensure our application has an SSL certificate for secure HTTPS traffic. For now, we'll hard-code the certificate name to keep things simple. We've started defining the domain name property for the certificate. However, before we finish assigning its value, we'll update our custom props interface to include a new property, DNS record name. The DNS record name property will be used in combination with the hosted zone name to form the full domain name. In our case, DNS record name will have the value demo, and the hosted zone name is pixelwake.com. Together, they create the full domain name, demo.pixelwake.com. Finally, we set up DNS validation by referencing the existing hosted zone. This ensures AWS Certificate Manager can verify domain ownership through Route 53. Now that we've set up the SSL certificate, the next step is to create the ECS resources needed to deploy our containerized application. Let's go through each piece. We'll be adding step by step. First, we'll create an ECS cluster. This cluster will serve as the orchestrator for our containerized workloads. It acts as the foundation where tasks and services are deployed. We'll use the cluster construct from the AWS CDK to set this up. Next, we'll define a Fargate task definition using the Fargate task definition construct. A task definition is essentially a blueprint that specifies how our container should run. It includes settings like memory, CPU requirements, and task roles for security. Once the task definition is in place, we'll add a container to it. We'll define it using the task definition, add container method. Here, we'll specify the container image, environment variables, and other configuration details needed to run the application. Finally, we'll create a Fargate service with the Fargate service construct. This service is responsible for managing the tasks, ensuring they remain running, and scaling them based on demand. We'll also integrate the service with our application load balancer to route traffic to the containers. Our first ECS construct to create is the cluster. A cluster is the central resource that manages and orchestrates the deployment of containerized workloads on ECS. It serves as the foundation for running tasks and services within your application. To set it up, we'll specify the VPC where the cluster will operate, ensuring it's in the correct network environment, and we'll provide a name for the cluster to keep it easily identifiable within our infrastructure. Next, we'll create a Fargate task definition, which defines the blueprint for running our containerized application within the ECS cluster. As part of the configuration, we'll set the memory limit in megabytes to 512. This memory is allocated to the task. This allows for ensuring the task has sufficient memory to operate efficiently. Additionally, we'll set the CPU units to 256, which provides 1/4 of a virtual CPU for processing. Next, we'll grant the ECS task permission to access our Docker Hub secret in the Secrets Manager. By using the grant read method, we ensure that the task can securely retrieve the secret when it runs. In this step, we're adding a container to the task definition, which defines how our application will run. The key properties being set include image. This specifies the container image to use for the application. In this case, it's pulling the Apache Web Server's latest image. Credentials are also configured for accessing private repositories if needed. Memory limit. This sets the memory allocation for the container, ensuring it operates with a defined limit of 512 megabytes to prevent overuse of resources. CPU. This allocates a 1/4 vCPU for the container, which is only useful for this demo. Logging. This configures the container to send logs to AWS CloudWatch logs with a stream prefix of Apache container logs. It also specifies that logs should be retained for 5 days. Now, we'll map port 80 to the container. This configures the application running inside the container to communicate with the outside world on port 80. By explicitly defining this, we allow the container to listen for traffic on port 80, allowing us to serve websites or applications. Here, we define a Fargate service. A Fargate service allows us to run containers without managing the underlying EC2 instances. We'll set a few properties on this construct, including the cluster. This groups our tasks together. The task definition specifies the container details like the image to use and required resources. The desired count, we set this to 2, meaning 2 tasks will always be running for redundancy and availability. And finally, we add a public IP. For testing, we allow the service to have a public IP. However, in production, it's better to keep services private and manage access through a load balancer. The Fargate service abstracts the complexity of infrastructure management, letting us focus on our application rather than the underlying servers. An application load balancer is created next, and its purpose is to distribute incoming traffic across the tasks running in our service. We'll deploy this load balancer into our existing VPC we referenced above. Next, we'll make this internet-facing. This makes the load balancer accessible from the internet, which is necessary for a public-facing application. The ALB helps with scalability, availability, and redundancy by ensuring traffic is routed efficiently across healthy targets. Here, we define an HTTPS listener with an SSL certificate. The port configures the ALB to listen for traffic on 443. Protocol, HTTPS, configures encrypted communication between clients and the server. The SSL certificate enables this encryption, ensuring secure interactions. We add another listener to handle unsecured traffic on port 80, but its primary job is to redirect this traffic to port 443. This way, all users are forced to interact with the application securely, which is a standard best practice for web applications. In the next step, we configure a health check for the targets attached to the listener. In this scenario, the targets are the Fargate service tasks. Let's configure the properties. Path. The ALB periodically checks the root path of the application. Interval. The health check runs every 30 seconds. Health checks ensure that the ALB routes traffic only to healthy containers, improving reliability and user experience. Finally, we create a DNS record pointing to our load balancer. Let's put the final touches on our stack by configuring a few properties. Zone. The hosted zone represents the domain we are managing in Route 53. Record name. This will be the subdomain or domain name users type into their browsers, in our case, demo.pixelwake.com. Target. The ALB becomes the endpoint for this DNS record. This step updates the Route 53 record to map the ALB to our subdomain. We're almost done. So far, we've created a custom AWS CDK stack to deploy an Apache Web Server into the cloud with ECS Fargate. This stack isn't just functional. It's a powerful example of how AWS resources can work together seamlessly to create a secure, scalable, and highly available application deployment. Now, it's time to take this and put it to use in the main TypeScript file. By creating a new instance of the stack class, we'll integrate it into our CDK app and make it ready for deployment. Ready to finish this up? Let's do it. Here's the plan. We're going to import the custom stack class we just created. Next, we will instantiate it in the main file, passing any required parameters like environment details or resource properties. We'll synthesize the stack into AWS CloudFormation templates, so it's ready for deployment and run the CDK commands in the terminal to deploy our app. To use the stack we just built, we need to instantiate it in the main file of our CDK project. This is where we define the stack's context, give it a unique identifier, and pass any custom properties it needs to configure resources. The first argument we pass is the app. This represents the CDK application context and connects the stack to the overall structure of our project. The stack is part of the broader app when we synthesize and deploy to the cloud. The second argument is the unique identifier for our stack. In this case, we'll name it ECS Apache Web Server Stack. This ID is how CDK recognizes the stack internally, and it also defines the stack name that is used when we run the CDK commands. The third argument is where we pass our custom properties. These props allow us to customize the behavior of the stack based on the inputs we provide. Now, we're going to fill in all of the required properties for our stack to work. The first prop we're passing is the environment object, which includes the account and region properties. These specify the AWS account and region where our resources will be deployed. We'll retrieve the account ID from the AWS console. This is the unique identifier for your AWS account. We'll specify US East 1 as the region. Setting the environment helps direct resources to the correct AWS account and region. Next, to find the VPC ID, we'll go to the AWS console, navigate to the EC2 console, and locate the ID in the VPC section. Using the VPC ID connects the resources to the appropriate network. The hosted zone ID identifies the Route 53 hosted zone where DNS records will be created. This hosted zone corresponds to the domain name we'll associate with this application. To find this, we'll go to the AWS console, navigate to Route 53, and locate the hosted zone we want to use. This property links the DNS configuration to the correct hosted zone. The hosted zone name refers to the domain name associated with the hosted zone, such as pixelwake.com. This value is paired with the hosted zone ID to define where DNS records are created. We'll locate this in the Route 53 console when selecting the hosted zone. This property aligns DNS settings with your domain name. Finally, the DNS record name sets the specific subdomain for the application, like demo.pixelwake.com. This value is used to create an A record in the hosted zone. The DNS record name provides a user-friendly URL for accessing the app. We've done it. We've created a custom CDK stack to deploy an Apache Web Server to AWS Fargate. Along the way, we configured a new CDK app and defined all the resources we need, including networking, compute, load balancing, and DNS setup. Now, we're ready to move on to running the CDK commands. Before we can run these commands, we need to authenticate with AWS. In my case, I've configured my AWS account to use AWS Identity Center with single sign-on. This setup allows me to generate short-lived access keys, which are ideal for secure, temporary access to AWS services. We'll grab a set of short-lived access keys from the AWS portal and paste them into the terminal window. That will allow the CDK to communicate with our AWS account. Now that we're authenticated and ready to go, let's run the necessary CDK commands to deploy our stack. We'll start with the yarn cdkls command at the terminal. This command lists all the stacks defined within our CDK app. As you can see in the terminal output, we have one stack to work with, ECS Apache Web Server Stack. This confirms that our custom stack is correctly configured in the CDK app. Next, we'll run the CDK diff command. This command shows a detailed comparison between the current state of our AWS infrastructure and the changes our stack will introduce. It provides a clear overview of the resources that will be created, modified, or removed. Once we've reviewed the output from CDK diff and confirmed that everything looks correct, we're ready to deploy. To do this, we'll run the CDK deploy command. This will synthesize our stack into a CloudFormation template, upload the template to AWS, and create or update resources as defined in the stack. During the deployment process, you'll see progress updates in the terminal as AWS provisions the resources. While the CloudFormation template is being deployed, we can hop over to the AWS console and watch the progress in the CloudFormation console. We can confirm that our stack is in the creation process. We can check for updates by refreshing the events log. Next, let's open two new browser tabs to check the ACM certificate and ECS resources. It looks like our SSL certificate has been issued already. Now we can check the progress of the ECS cluster, service, and tasks. As you can see, the tasks are coming online. This is great. So far, things are working well. And there we have it. We have two running services in ECS. Let's check the browser to see if the website is up and running. It's time for the big reveal. And there you have it. It works. Using the AWS CDK and TypeScript, here's a quick recap of everything we accomplished. Get references to AWS resources. We started by gathering the necessary AWS resource details, such as the VPC ID and Route 53, hosted zone information, ensuring our infrastructure aligned with the environment we're deploying to. Create an SSL certificate. We generated an SSL certificate to secure the application with HTTPS, adding an extra layer of protection for users accessing the server. Set up ECS Fargate resources. We created the ECS Fargate cluster, defined the container configuration for the Apache Web Server, and set up tasks for a scalable, serverless container environment. Configure an application load balancer. We added an ALB to manage incoming traffic, set up HTTPS listeners, and added health checks to maintain application availability. Attach a custom domain name. Finally, we used Route 53 to associate a custom domain name with our ALB, making the application accessible via a user-friendly URL. Thank you so much for watching. I hope you found this tutorial helpful and that it gave you a solid understanding of how to deploy a Docker image to AWS ECS using the AWS CDK. If you enjoyed this video or learned something new, please give it a thumbs up. It really helps the channel. If you have any questions or suggestions for future topics, feel free to drop them in the comments. Thanks again, and I'll see you in the next video.